Blind. All right, today we're going to talk about Chapter 6, inner product lengths and orthogonality. And here's a definition of an inner product. And here's some properties for the inner product. And let's ignore the side notes over here. We have the length of the vector is the square root of v dot v. And then you can normalize a vector to make it into unit length by dividing it by the magnitude of that vector. And so that's it. We're all caught up. All right. Here are some examples that we're working on. We took v dot w. If we let this equal to v and let this next vector equal to w, and we've computed v dot v, the magnitude of v, and then we normalized v. So, okay. Yes. Right. Yes, yes. Yeah. So there's a lot of ways to look at this. You can use parentheses. You can treat these as if they were just points, and then you can think about dotting points. But the way that we formally introduce the inner product is we're using, quote, matrix multiplication. So, but I don't think it's any harm if you think about it another way. Like if you've taken Calc 3, if you want to think about the dot product that way, that's no problems for this class. All right, let's move on to the distance. Finding the distance between two vectors is geometrically, or using what we know as the distance, it's the same as finding the distance between 2 points, or we can think about it that way. So remember that vectors are essentially these directed line segments from the origin. They don't have to be, but you can always place them back to the origin. And then the way these points, or the way these vectors are defined, these are the points that are essentially equal to the vector. So when you say the vector 1, 1 in R2, you're essentially looking at a vector in standard position. Its tail is at the origin. And then the head, or the arrow, is going to be pointing at the point 1, 1. Or did I say 1, 1 or 1, 2? 1, 1. So this distance between two vectors is essentially the distance between the heads of those vectors, which is essentially the distance between these 2 points. The reason why we want to refer to them as vectors is that we can technically find the distance beyond just R2 and R3. We can take a look at R5 in a 5-dimensional space, and we can say the distance between these two vectors would be this by definition. Yeah. That'll help us find lengths of stuff. I mean, this is essentially finding the length as well. It's like finding, well, that's how it's defined. The distance is equal to the length of the difference between those 2 points. And so that weird, the weird definition with the functions, or the integral from 0 to 1, technically we can find distances between functions the same way. Whoa, I don't know. It's just an abstract way of looking at distances. Yeah. Well, the distance isn't going to be length anymore. I mean, the distance is going to be how far how far apart the two vectors are.
But we don't know what these vectors even look like.
You can't visualize it, no, but I mean, you have representations of them.
So the one thing would be, can we find applications where the integral two functions are equal to the constant bound equal? What thing comes? There are some things in the lab, there's some examples where you take the product of two functions and you go to one constant bound equal. For your series,
Only.
Oh yeah. If the vectors all have to be in the same vector space.
Yes, yes. Yeah, so that's important. The vectors have to be in the same vector space. Because if you're, technically, you can fill some of those vectors in with, some of those components in with zeros. Like if one vector is in R3 and the other one's in R2, you technically cannot find the distance between them. Unless you set up a convention that says that one of the components is equal to 0. And then maybe you can think about it that way. But then when you say one of the components is equal to 0, does that mean it's the last component, the first component, or the second component? So it still would leave some confusion. So I think the best answer is yes, they have to be in the same vector space. Okay? Yes? Correct. Yes. So u minus v, this should equal to v minus u. Because, yeah, you're going to find a difference and then square them and then take the square root. Yeah. Because you're looking at a distance and the distance has no direction. It's just a particular length. Yeah. So whether this arrow is going which way or that way, it doesn't matter because you don't care about which way it's going. You care about the length of it. All right. So let's do a quick example. Let's do number 14. Where we have a couple of vectors, we'll find the distance between those two vectors. And in R3, you can take a look at these vectors, quote vectors, as vectors in standard position, which means you're really measuring the distance between the 2 points. So the distance is going to equal to, well, you know the distance formula, right? 0 minus -4 squared plus -5 minus -1 squared plus 2 minus 8 squared. So this is the distance formula, and if you think about this as vectors, you can say u minus v. Is that v or z? It's z. Is going to equal to the vector 0 minus -4 minus 5 minus -1, 2 minus 8. So this is +4, -4, -6. And then the magnitude of that, or the norm, or the length of that, is equal to, you dot it with itself, 4 minus 4 minus 6, 4 minus 4 minus 6, and then you take the square root. So when you take the dot product, you get 4 times 4, 16, 4 times 4, 16, 6 times 6, 36. Now whatever this turns out to be. Anybody? What? 68? So this should also be square root of 68. So that would be the distance between those 2 points. Okay? All right. Any questions? Yes. Parallel? More like orthogonal. There's a lot of mirroring here. Speaking of orthogonal, say orthogonal. I said orthogonal. So we get to the orthogonality part, and notice that to be able to talk about orthogonal in a more abstract sense beyond R2 and R3, we need to define this whole idea of the dot product, because that's how we're going to define orthogonal. We're not stuck in R2 or R3, so when we say orthogonal, we don't tend to think of perpendicular or 90-degree angles, although you can if you want. But when you go beyond R2 and R3, then the whole idea of 90 degrees seems a little bit more difficult to kind of handle. So we use the word orthogonal. And the definition of orthogonal, according to this, is that the dot product has to equal to 0. So I think in Calc 3 or in a geometry sense, we think about perpendicular first, and then we define the dot product, and then we say, oh, if dot product is equal to 0, it means that vectors are perpendicular. And so that thinking is kind of going a little bit backwards from the way we need to think about it. And we need to think about orthogonality as coming from the dot product and not the idea of an angle. So two vectors are orthogonal if the dot products equal to 0. That's the definition. Okay? Yeah.
So can we say that it is possible to have a dot product of two vectors that are not in the same vector space? For example, if let's say U is 1 by 3 and V is 1 by 4, and the transpose of U is going to be 3 by 1. We might not. Of course we cannot have a dot product between the 1 by 4 matrix and the 3 by 1 matrix, because the middle part doesn't match. But we can have a 1 by 3. We can have a 4 by 1 times 1 by 3 or something like that. So that would get.
So that kind of looks at the outer product, not the inner product.
Yeah, but if you have like a 4 by 1 matrix, in the end will become a 4 by 3.
Right. So I think that's what we define as the outer product. Yeah. So that when you do it the other way, where your answer is not a scalar, your answer is a matrix, then that's not the inner product anymore. Yeah. The inner product is always a scalar. That's an important part. So sometimes the inner product is called a dot product, but remember the other word for the inner product is sometimes it's called a scalar product, because the result needs to be a scalar. All right, let's check one of these to see if it's orthogonal. Let's just check the number 16 here. So we take U dotted with V, and if we do this enough times, you'll see that you're really just multiplying component by component and adding them together, right? And so that's when you start looking at it like a vector in Calc 3 or something. So we have 12 times 2 plus 3 times negative 3 plus negative 5 times 3. So this is, what is this, 24 plus minus 9 minus 15. Does that add up? 0. So we can say U is orthogonal to V. Okay. Pretty straightforward, pretty simple, yeah. Then you can practice, you can check, or I guess you do homework, you'll get a couple of these problems where you have to check if they're orthogonal. Like the perpendicular sign? They generally, yeah, I guess they do. Yeah, let's say yes. Because that would have been a lot quicker to write, right? Now it looks like they're perpendicular. Oh, boy. The thing is that it's all connected. It's just different conventions for different applications. All right, let's see. There's this idea of trying to invoke Pythagorean's theorem out of this. It says two vectors v, u, and v are orthogonal if and only if this is true. We can think about what would happen if they're not orthogonal and how that would turn out to be. But if they are orthogonal, then this must hold. Right. So we haven't been proving much. I think I was going to try to make a point to do more proofs. So let's see if we can prove this. We use the definition of the magnitude of v is equal to the square root of v dot v. So then the magnitude of v squared is just v dot v without the square root. Right? So let's take a look at what happens here. You got v plus v, or this is u v. U plus v dotted with u plus v is equal to, well, let's worry about the other side in a minute. So this is u plus v is a vector, and then we're taking the dot product, and then we're going to distribute. So we're essentially going to FOIL this, but technically if we do the distribution, we do it one by one. So this would be u plus v dotted with u plus u plus v dotted with v. And this is equal to, redistribute again, u dot u plus v dot u plus u dot v plus v dot v. So what we have here is the magnitude of u squared, and then here are two dot products that are essentially the same because it's commutative. And then we have the magnitude of v squared. So we want this to equal the magnitude of u squared plus the magnitude of v squared, but that's only going to work if this middle term is equal to 0, right? So equal if u dot v equals 0, and that is the definition of orthogonality, is that should put that perpendicular sign there. So there's a quick proof. And then if you can visualize this, visualize u and v vectors, and then the u plus v would be like it's diagonal or something like that. And then you can make a right triangle out of that. All right. So now let's go a little bit beyond vectors and take a look at subspaces. This is where it gets a little heavier. I use that perpendicular sign after all. So if we have a vector z is orthogonal to every vector in a subspace W, then z is said to be orthogonal to W. But that's a thing about orthogonality. We defined orthogonal as being orthogonal between two vectors. Now we're saying a vector can be orthogonal to a whole space. So that's the difference here. The set of all vectors z that's orthogonal to W is called the orthogonal component of W. So the orthogonal complement, thank you. The orthogonal complement of W. And is denoted by W with a superscript of that perpendicular sign. So that's called W perp. Perpendicular. W perp. Perpetrator. So, a simple example of this is that if we have, I don't know, if we have, we could take it really simple. So let's let W in be a subset of R3, where W is the XY plane. So we're in R3, so we can visualize this. So how can we visualize this? Let's see. So W is the XY plane. So this is W. Right? So can you give me an example of a vector that's perpendicular to that? Let's pick an actual vector. 0, 0, 1. So the vector 0, 0, 1 seems like it would be perpendicular to that, right? So can you give me another vector that's perpendicular to that? 0, 0, 2 is another vector that's perpendicular to that. So what is W perp? What? It's a z-axis, span of 0, 0, 1. How can we write the span of 0, 0, 1? Any Calc 3 people here? So constant multiple of t times k. So if you let t be some arbitrary parameter, t can be anything, right? And then k is that vector 0, 0, 1. So 5 times that would work. 7 times that, negative 3 times that, negative 254 times that, times k. So W perp would be just essentially that line passing through the origin that's parallel to the z-axis. So if your W is the xy plane, then W perp is just going to be this line. Yes, you can. Yeah. So the idea is that now that we're thinking about this as a vector or a subspace, we can take any of these vectors and move it around anywhere, and it would still be perpendicular to the xy plane. Okay. So from here, they're going to break this down a little bit and let W equal the span of a couple of vectors or something like that. And then they're going to say that anything in W perp would be perpendicular to anything in W. And that would make sense for us. Yes? Okay.
Is our subspace just two independent vectors? So it's like orthogonal to other vectors? Like is our W is what?
So our W is xy plane, right? But we could also think about W as being W. The xy plane is a two-dimensional geometric object. So we can think about this as being spanned by two linearly independent vectors. And the simplest two linearly independent vectors I can think of are the I and j vectors, right? So we can span with I and j. We can say W is equal to the span of 1, 0, 0 and 0, 1, 0. And that means any linear combination of a vector in W perp is going to be perpendicular to any linear combination of vectors in W. So if I generically pick another vector in W, so let's say V in W, and let's say V is equal to about as generic as I can get. I can have any number for X and any number for Y, and Z is equal to 0. And if I dot that with any vector here, W, let's say U, in W perp, that's perp, then maybe generically, about as generic as I can get, this is going to be some 0, 0. I could do this because this is a really simple example, but in more complicated examples, the generic stuff would be a little bit more difficult. But in any case, if I have a vector in W perp and have a vector in V, you see that any vectors in W perp get dotted with any vector in W is going to, when you take the dot product of these two, it'll be 0, right? So 0, 0, and 0. So that's just going to end up to be 0. And that's what we're going to show or state in the next couple of theorems or whatever. All right, so let's see. Some properties. So if W is a subspace of Rn, then the vector X in W perp, if and only if it's orthogonal to every vector in the set that spans W. So we kind of mentioned that in our really simple example. And then not only that, but W perp is also a subspace of Rn. Remember subspaces? Could, but do you remember subspaces? There's like two important properties of a subspace. Bob? Well, let's take a look at the properties of subspaces. Nate, were you gonna say something? Okay. Properties of subspace. So it has to be within the subspace. So if U and V are in W, then what? U plus V is also in W, and C times U is also in W, right? Yeah. For any, yeah. So W perp is supposed to be a subspace of Rn. Let's see if we can prove that. So how we're going to prove this? So we have to pick a couple of vectors in W perp. So let U and V be vectors in W perp. Okay. We should also let Z be some arbitrary vector in W. Okay. So it's given that U dot with Z and V dotted with Z are both equal to 0 because they live in the perpendicular world, right? So now we have to prove that this is true. Then A, U plus V. So if this U plus V is still going to be in W perp, then that means the dot product of U plus V should equal to 0 as well. But according to the distribution property of the dot product, U dot Z plus V dot Z is, well, U plus V dot Z should equal to U dot Z and V dot Z. But we know that this is given, so these are both equal to 0. Okay, so this statement proves that U plus V is in W perp. Okay, so we're halfway there. To prove the second one, we're going to multiply one of these vectors. Let's multiply U times some scalar C. And then we want to know if that's in W perp. So we're going to dot it with Z to see if it'll work out. Well, another property that we have for the dot product is that we can reassociate with a scalar multiplication and consider U dot Z separately from C. And that's C times 0, which is equal to 0. And then so we've managed to prove the other part. Okay, so those are the two requirements for it to be a subspace, and we've just shown that it actually works out. So that's the proof. Hey, look, we're proving things now. People usually find a cool way to end their proofs. Or you can do QED. I usually just put double slash and then that's it. That's therefore, so that's, yeah, that means therefore. Box, this is a way that most textbooks tell you that that's the end of the proof. Yeah. I don't know. We can't be doing aggressive stuff since we're just starting to prove things and like 2/3 of the semester is over. So I had a professor in college who always do these proofs and then always write QED. And at some point, somebody asked, "What does QED stand for?" And he didn't know. So I always had to make sure that I know. So that which was to be proven. Anyways, so yeah, there's a couple of important properties for the W perp. More important is that it's actually a subspace as well. There's another. So a couple of subspaces, or a handful of subspaces that we did study a lot was the row space, the column space, and the null space. So because they are subspaces of a matrix, it turns out that they have some interesting properties. So an M by N matrix, orthogonal complement to the row space is a null space. So that means the row space, perp, the orthogonal complement of the row space is actually equal to the null space. So, and they come from the same vector space. So the row space and the null space are subspaces of the same vector space. Now the column space is a little bit different, but if you just take the transpose of the matrix, then the column space is essentially the row space. So we can take the column space would be the orthogonal complement of the column space would be the null space of the transpose of the matrix. So in fact, one of the questions that was on the midterm on the exam number 2 was, what is a row space a subspace of, and what's the null space a subspace of? So the row space and the null space are subspaces of the same space. And the column space is a subspace of, well, if it's not a square matrix, it'll be a subspace of a different space. All right. So I wanted to come up with an example of this, but I forgot. So, and we need to, we're supposed to have 6.2 done by now. So let's introduce a couple of concepts in 6.2. This will get us ready for more Calc 3 stuff. No, we just have the final exam. Hopefully by next week. Yeah. Yeah, we'll talk about it after I grade the second exam. Yeah. No. So another whole bunch of definitions here. Let's take a look at the definitions. If you have a set of vectors, you can say that the set of vectors is an orthogonal set if each pair is orthogonal to each other. So a simple example would be like the ijk vector. Yeah, the ijk vector in R3, they're all orthogonal to each other. Sometimes we say they're mutually orthogonal. If there's only two vectors, you could say, yeah, they're orthogonal to each other. If there's three or more vectors, then you have to kind of check all the different possible combinations to make sure that they're orthogonal. Well, it depends. In this case, they're just talking about p vectors, which is not necessarily the same number. So it doesn't have to be the whole thing. Like in R3, if I just consider two vectors that are perpendicular to each other, then that's just a two-dimensional subspace. At most, then, yeah. So they're mutually orthogonal if you take the dot product of them is equal to 0. But if you take the dot product of itself, remember that that's not necessarily equal to 0. So that's why they say all the dot products of those combinations as long as I is not equal to j. So there's a theorem over here that follows. If you have an orthogonal set, is a set of non-zero orthogonal set of non-zero vectors, then S is linearly independent and hence a basis for a subspace. Because they're mutually orthogonal, right? You can't have any combination that's going to be a linear combination of another, because they're all orthogonal to each other. And again, think about that in 3 dimensions. What? It seems like it's obvious, but it needs to be stated. So you have an orthogonal set, then they're going to be linearly independent. And because they're linearly independent, then they form a basis. In this case, since there's p vectors, we can say this is a p-dimensional subspace of Rn. So definition, an orthogonal basis is basically a set. It's a basis that's also orthogonal. Seems obvious. Yeah, so if it's a basis and it's orthogonal, then we'll call it an orthogonal basis. Don't look any deeper than that.
So, let's suppose you're trying to identify points in 3 for this. Would you rather find the point 3, 2, 4 in the regular basis vectors where you have x, y, and z, or I tell you your equations are -1, 2, 6, like -8, 4, 7, and a bunch of random vectors, you can solve the matrix to find out where you are. Right? That's a whole lot easier.
Well, let's throw this one other theorem over here. Because it's a basis. It's not just a set, it's a basis. Yeah. I told you, don't look any deeper than that. It's a couple of names, and then put it together and say this matches the definition. All right, this last one is a little trickier. It's good to have a visual of this, and since we don't have time, we'll do the visual next time. If you have an orthogonal basis for a subspace, then each y in that subspace can be written as a linear combination of those basis vectors. Or y is a vector in that subspace. Yeah. So think about it this way. You're flying a drone in space, right? And then you're moving in a certain direction. So you have a particular direction vector, a velocity vector. And now you want to figure out, you want to hit a target that's somewhere else in space. And so what you want to do to try to hit that target is you want to hit that target based on where you are and how you're oriented, right? You don't want to go back to the origin, wherever the origin might be in space. You want to set your position as your own origin. So now you're going to make up 3 vectors based on where you are and which way you're going, so that you can say, from these 3 vectors, I want to hit this other target. Now, these 3 vectors would be best if they were orthogonal to each other. Not only that, we'll see that it's even better if they were orthogonal and all of unit length. Because now you have your own ijk in your own position, and then you can spot something based on your own new ijk that you're going to hit your target with. Okay? So think about that for these types of orthogonal projection problems. Yeah? So do I.
Well,